Dear students, welcome you all to today's teaching program. Now, today we are going to discuss about the chemical reactions of haloarenes. So, please you look to the word haloarene. This word comprises of two words, halo and arene. The word halo refers to the halogens. Halogens means fluorine, chlorine, bromine and iodine. And arene, the word arene refers to a aromatic compound. Dear students, whenever we tell about a aromatic compound, immediately the structure of benzene comes to our mind. Actually, as you know, the aromatic compounds, they follow the 4n2 number of pi electrons. So, the benzene molecule, for example, it has 6 number of pi electrons. You please see the slide here. You will find that in the structure of benzene, there are 6 number of carbon atoms present at each corner of this hexagon, and they are joined to the hydrogen atoms. But you may find out that the double bonds which are present between the carbon and carbon, they are not fixed. You please look to the picture carefully. What you have find out here? They are present there alternatively. But dear friends, any of these two structures is not a correct one, because you may see in the next thing I had shown you, there exists a pi electron cloud. So, let us be very clear about this pi electron cloud. Actually, what happens? Each carbon atom of benzene is sp2 hybridized. Each sp2 hybridized carbon atom has 3 number of sigma bonds formed by it. But what happens to the left one p orbital? The p orbitals which carry single electrons, they undergo sidewise overlap. You may see from this picture, they undergo sidewise overlap to form the ring as shown in the picture. Okay. So, always remember that the benzene ring has one pi electron cloud which is negatively charged, and the pi electrons are not fixed at a particular position. Please mind this sentence, this statement again. The pi electron cloud is not fixed at a particular position. It spreads itself throughout the ring, and we call it that it is delocalized over the whole chain. This is the essence of an aromatic compound, and all the properties the benzene ring shows us are because of these pi electrons. Okay. Then students, next you see how we will get a haloarene from a benzene. If by any means we replace the hydrogen atom of benzene by a halogen atom, then we will get a haloarene. And then also you should know the ortho, meta and para positions of the benzene ring. So, what are ortho positions, meta and para positions? Suppose our halogen group is present as shown in the picture, then just the position next to that R group is known as ortho, and if we take the position of R as 1, then the one which is present at position 2, that is 1 to 1 position is halo and 2 position is something else, that is 1 2 position is ortho and 1 3 position is meta and 1 4 position is para. Then let me recall your memory about the nucleophiles and electrophiles. You just split this word nucleophile. What you will find out here? What is a nucleophile? Just split that word to two halves. The nucleophile, when we split it, we get two words. One is the nucleus and the other one is philic. So, nucleus is a positively charged species, all of us know it, and philic means loving. So, those species which may be neutral molecules or which may be rich in electrons, which may be negatively charged species also, which have the tendency to donate a pair of electrons, those are known as nucleophiles. Please again listen this word, because it is a very crucial word which we are going to use throughout our process. So, the word is nucleophile, nucleus loving. Which particles are, which species are nucleus loving? If they have more number of electrons to donate. For example, I have given you the structure of ammonia. So, you all know ammonia is a very good Lewis base. So, the electron rich species which have the ability to donate a pair of electrons are called as nucleophiles. Example is ammonia, and also you may see the cyanide ion, also fluoride, chloride, etc. They are also the nucleophiles. Then come to the next slide, the electrophiles. What are the electrophiles? Similarly, split the word, very simple word, electrophile, electron loving. So, electron is a negatively charged thing and phile means filling. So, those species which love electrons, which love negatively charged species, which one will love? Those which have the positive charge with them, they are the electrophiles. So, it is very clear to you. So, those species which have vacant orbitals to accept the electron pairs, they are the electrophiles. So, which are the electrophiles? Just guess and tell me. The Lewis acids like BF3, like H plus, like Br plus, like Cl plus, which can accept the electron pairs. So, you just see the structure of BF3 in the slide. So, what you have seen? The central boron atom, it is surrounded by 3 bonds, means each bond carries 2 electrons. So, around boron there are 6 electrons present. So, 6 electrons are present around the central boron atom. So, as 6 electrons are present around the central boron atom, as per the octet rule, it bonds to complete its octet. So, how it will do it? It will have a tendency to gain a pair of electrons. Similarly, suppose Cl plus, you will know Cl has the electronic configuration 287. So, if it will lose one electron, it will become Cl plus. So, when it will become Cl plus, it is 286. So, in this case, it can also accept a pair of electrons. So, chloronium ion, all of you are acquainted about the chloride ion, but here I am telling you about a new type of species, the chloronium ion, deficient of electron. So, these are some of the examples I have given: the proton, the bromonium ion, chloronium ion, which are the examples of the electrophiles. Then so students, let us test your knowledge, how much you had understood, grasped about the electrophiles and nucleophiles. Try to identify the species from them which are the electrophiles and which are the nucleophiles. Okay. So, I have given you the answers. The Lewis acid, suppose BF3, H plus, Cl plus, they are the electron deficient species. So, they are the electrophiles. Similarly, ammonia, F and cyana, F minus and Cn minus, they are nucleus loving species. So, they are the nucleophiles. Okay. Then we will go to the nucleophilic substitution reactions of haloarenes. Actually students, you have already studied about the nucleophilic substitution reactions of haloalkanes, and also you know that the haloalkanes, they are very much prone to the substitution reactions. But now I want to show you that suppose in a beaker you have taken a alkyl halide, suppose that is methyl chloride with sodium hydroxide. The reaction takes place at ordinary conditions, but at the same time under the same conditions, if we try to do the same reaction, the substitution reaction, nucleophilic substitution reaction, the aryl halide cannot do that reaction. So, I have summarized the reactions which you had studied before. The alkyl halides, they are capable of undergoing SN1 reactions and SN2 reactions, which have already taught to you in the previous class. But these aromatic compounds, this particular type of compounds which possess the benzene structure, the pi electron cloud, those compounds only under drastic conditions they also give substitution reactions whose name is SNAR, which stands for aromatic nucleophilic substitution reaction. So, next this implies that the haloarenes, they are not very much prone to the SN reactions. So, what are the reason behind it? Why do the haloarenes, they are not so much prone to the nucleophilic substitution reactions? There are so many reasons, and we will discuss the important reason first. The first reason is the resonance effect. Please see the resonance structures of this chlorobenzene. In this case, the chlorobenzene, it has the chlorine atom substituting the hydrogen atom of the benzene, and in this case there are lone pair of electrons present on it, and it satisfies the condition for conjugation. So, the electron pairs, they undergo conjugation with the benzene ring and hence make it ineffective for the further reaction. I will explain you detail further. So, students, we had discussed the comparison between alkyl halides and aryl halides, and what I had told you that aryl halides, unlike the alkyl halides, are not so much prone to the nucleophilic substitution reactions. Only under drastic conditions they show such reactions. why it is so? Why do the aryl halides are reluctant towards these nucleophilic substitution reactions? Let us understand those reasons. So, as I had told you, the first reason is the resonance effect. So, let us see the resonance structures of chlorobenzene. Students, if you know how to draw the resonance structures, then it is okay. But if you do not know how to draw the resonance structures of a particular compound, then please draw with me, so that you will also be habituated with it, and also you will understand the meaning of these resonating structures, which is very much helpful for you to understand the reaction mechanism of these aromatic compounds, not only for aryl halides, for all aromatic structures compounds. To understand the mechanism, drawing of all these resonating structures is very much crucial. So, please draw with me. There are these structures. You please see this structure, the structure 1. What you have seen here? The chlorine atom is joined here and it has 7 electrons. With the use of 1 electron, it forms a bond. It has already 3 pairs of electrons along with it. So, what happens? In this situation, the condition of resonance occurs, because we call this concept actually the conjugation. What is the conjugation? If lone pair is there and single bond is there and double bond is there, they are alternate to each other. Let me repeat, the lone pair, single bond, double bond, when they are alternate to each other, then the concept of conjugation comes to picture. That is, this lone pair of electrons, they may be donated to this single bond, and thereafter what happens? What happens to this carbon atom? You see, already there was one bond, and because of this electron pair, there becomes another bond. So, there are 2 bonds, here 2 bonds 4, here 1 bond. How many bonds there all total? There are 5 bonds. So, carbon can show only 4 bonds, 4 valency. Its valency cannot be exceed to 4. So, when this carbon atom, now we call that this carbon atom is under strain. So, it will try to relax its charge. So, what happens? It will try to break the weakest bond. Which one the weakest? This is this pi bond. So, these pi bond electrons, they shift towards this carbon atom. So, this is the charge. This is the result. You just see what I am doing. I am just shifting these pi electrons to this particular atom. So, what happened here? Now, here the minus charge developed, and you may see all these structures are as before. Now, what happens? Again this carbon, it also disperses this to this bond, and similarly this carbon atom become overstrained. So, it releases its electron pair to this carbon atom. So, again in this structure 2, what you had seen, these electron pairs are coming here, and now here because of this the double bond is formed. And what happened here? Here the minus charge is there and everything is as before, but again in the next step this electron pair goes here, and similarly this bond breaks and these electrons go here, so on. So, all these structures thus formed are known as the resonating structures. So, if we are able to write the resonating structures of a particular compound, then that compound is stable. So, what you had seen through these resonating structures, a partial double bond character developed between carbon and chlorine, which was not in case of carbon and chlorine for the alkyl halides. So, that is why a large amount of energy is required to break this bond. Because of this reason, the haloarenes, they show low reactivity towards the nucleophilic substitution reactions. And now we will come to the second point, another reason. In case of alkyl halides, as you all know, the carbon atom was sp3 hybridized, but in this case the carbon atom is sp2 hybridized. So, in the haloarene the carbon atom is sp2 hybridized, means the S character is more here. So, as the S character is more, so the electrons of the chlorine atom or any halogen atom, that is pulled more inside towards the carbon atom. So, its bond length is small, and again it is difficult to break. And so I have shown you one example. In case of chlorobenzene, the bond is less polar, whereas in chlorocyclohexane the bond is more polar, means the electrons are more shifted towards the electronegative chlorine atom. Then another reason also, the instability of the phenyl cation. If by any reason, suppose the carbocation is formed due to loss of the Cl ion, then what happens? This particular structure is not stabilized due to resonance. So, because of all these reasons, the compound is not very much prone to the nucleophilic substitution reactions. However, under drastic conditions, the haloarenes are able to form some important compounds, and in that case one condition is that the nucleophile which is attacking, it should be a strong one. First example, preparation of a phenol. This method we have described here is famously known as Dawes process. In this process, the chlorobenzene reacts with sodium hydroxide at very high pressure and high temperature to give the sodium hydroxide, which again subsequently reacts with dilute HCl to give us the product phenol. And also we can get aniline from chlorobenzene by making it to react with ammonia and cuprous oxide. You please note down this equation. Similarly, bromobenzene reacts with cuprous cyanide at high temperature to give the product cyanobenzene. So, these are some of the reactions of the aromatic halides, and then of giving, or if they will give the reactions only under drastic condition, or there is some other solutions to it. That thing I want to tell you. You just see the slide what we had written. Reactivity of haloarenes in presence of electron withdrawing group. So, now we are introducing the new word, the electron withdrawing group. Actually there are some groups like nitro, cyano, etc., which are highly electron withdrawing in nature. The presence of such groups makes our process go in a faster way. So, students, please practice all these equations, and in the next class we will discuss many interesting factors about these nucleophilic substitution reactions. Now, we are going to discuss the reactivity of haloarenes in presence of electron withdrawing species, in short very commonly known as EWG. So, please first analyze this word electron withdrawing group. Actually, there are some groups like nitrite, cyanide, etc., which have the tendency to withdraw the electron cloud from the benzene ring towards themselves because of their structure or because of their chemical nature. So, in that case their withdrawing nature affects the chemical properties of the aryl halides. So, ring becomes activated towards the nucleophilic substitution reactions, and if such groups are present in more number, then the rate of reaction increases. So, why do this happens? I can explain you through its chemical behavior. You just see the presence of nitro groups at ortho and para positions withdraws electrons from the benzene ring and facilitates the attack of the nucleophile, because previously as you had known that the benzene ring was a rich source of electrons. So, it was itself behaving as a nucleophile. So, it was not favorable for the attack of a nucleophile. I think you are following my point. If you are hungry, then you will need food. If already you have taken sufficient meal, then you will not like to take more food. That is the reason, that is the simple reason. Actually, the benzene ring has the pi electron cloud present on it, which is negatively charged. Again, nucleophile, it is also negatively charged. So, the benzene ring is negatively charged, the nucleophile is negatively charged. So, the attack is usually not favorable, but if by any means we are able to reduce the negative charge on the benzene ring, then that process will be facilitated. So, what we do? We just join one electron withdrawing group to the benzene ring, so that that group takes away the electrons from the benzene, decreases the density of the electron charge on the ring, and the process is favored. This thing you can understand by following this all these mechanism, all these structures. You just see the resonating structures. In the first structure, what you are seeing? The chlorine atom possesses the lone pair of electrons which are shared by the benzene, and if you will see deep to the structure, you will see that at ortho position the minus charge is formed, and also at para position the minus charge is formed. If we join a nitro group at this ortho position or para position, then what happens? This nitro group itself takes the electron cloud from it. Why it does so? Because you may see the nitrogen atom is in return, it is joined to the oxygen atom. So, the oxygen atom is also more electronegative than nitrogen. So, that electron cloud flows. So, as a result what happens? There is a net decrease in the electron cloud of the benzene ring. In case of ortho and para structures, one of the resonating structures carries a negative charge on the carbon atom bearing the NO2 group. So, these carbon ions are stabilized by the NO2 group. However, in case of the meta position, there is no such negative group. So, carbon ion of meta structure is less stable. Here I have given you a comparative attack at different positions of chloronitrobenzene. You may see in the first case it is the ortho position with respect to the Cl atom where the NO2 group is joined, and here the nucleophile which attacks is OH minus. You may see the temperature at 130 degree centigrade, this reaction is taking place and the Cl group is replaced by the OH group. Whereas, in case of para also the same product is obtained, only the NO2 group is placed at the para position, whereas in case of meta the product is not formed. So, we may summarize the mechanism that whenever a nucleophile attacks the nitrobenzene, then a complex is formed which is known as Meitner-Heimer complex, which undergoes thereafter which undergoes the cleavage of the carbon halogen bond and aromaticity is restored and the nucleophilic substitution takes place. Okay. So, what you had studied from this? The rate of the nucleophilic substitution aromatic reaction is, you may see that the first step in SNR mechanism is the slow step, as there is a loss of aromaticity of the benzene ring. You just see the first process, whereas we know that which one is the slow step, that is the rate determining step. So, in the first step which two molecules are involved? The haloarene molecule as well as the nucleophile, both of them are involved. So, but in the second step aromaticity is regained. So, it is a fast step. Therefore, rate law is written as rate is equal to K into concentration of the ARX into concentration of the nucleophile. Then increasing reactivity of nitro groups. You just see I have given a comparative account of all these. Chlorobenzene at 350 centigrade gives you the phenol, and this one the para substituted chlorobenzene, it gives the reaction at 150 degree centigrade, and if two nitro groups are present there at ortho and para positions, then the reaction takes place easily only at 100 degree centigrade, and if the chlorobenzene is substituted by 3 nitro groups at ortho and para positions, that is 2, 4, 6 trinitro-chlorobenzene, you may see that the product is formed even at hot water, that is at 30 degree centigrade. So, these things prove that the presence of nitro group, it increases the rate of the reaction. So, here I have given you some examples, some questions to test your knowledge. You please see at the question. After discussion of all these things, so I may ask you a few questions, like you please note down the questions and write their answers, we will discuss them later. So, students, we had discussed about the conditions under which the nucleophilic substitution reaction took place. So, we have taken few examples to just enhance our knowledge and to test how much you have gained from all these discussions. So, please see the question. The first question, which of the following shows more reactivity towards the SN reaction? So, you see I have given you two compounds. One is the chlorine atom is here 1, 2, 3, 4. So, what is the name of this compound? 4-nitrochlorobenzene. And what is the name of this compound? 4-nitrochlorobenzene. So, what question is asked you? Between these two compounds, which one will show more reactivity towards the OH minus, towards the nucleophilic substitution reaction? So, how you will approach this problem? So, if you had understood its mechanism, then it is very much easy for you, and if not, then please listen, I am going to tell you the answer. So, you may see that this nucleophilic aromatic substitution reaction, it takes place in two steps, and the rate determining step of this one, which is the slow step, it involves the attack of the OH minus group to the ring. Where do this OH minus ion attacks the ring? As I had shown you, it attacks at that center where some plus charge is there. You just see this bond, carbon and fluorine. So, fluorine being more electronegative than carbon takes the electron pair towards itself. So, a delta plus charge arises here, that is why OH minus attacks here. Similar is also the case here, the OH minus attacks here as the Cl minus attracts the electron pair towards itself. So, where do the rate of reaction will be more? If the magnitude of this delta plus charge will be more, then the readiness for attack will be more. So, in which case the charge delta plus magnitude will be more? It depends on the electronegativity of this atom. So, as fluorine atom is more electronegative than Cl, so the magnitude of delta plus here is more. So, what is your answer? This one has more reactivity than the second one. Then go to the second question. So, what was the second question? So, please see 2,4-dinitrochlorobenzene or 3,4-dinitrochlorobenzene. Among these two, which one will show the reaction, substitution reaction more easily? You just first draw the structure of 2,4-dinitro and 3,4-dinitrochlorobenzene. So, 1, 2, 3, 4. So, what is the structure? 2,4-dinitrochlorobenzene. And what is this structure? 1, 2, 3, 4. So, it is 3,4-dinitrochlorobenzene. So, what we had discussed till now? Whenever a nitro group is present ortho with respect to Cl, or if a nitro group is present at para with respect to the halogen, then what happens? It have very strong effect on withdrawing the electron cloud towards themselves, and they enhance the rate of the reaction. In the first structure, what you have seen, these two NO2 are substituted at ortho position as well as the para position. Whereas, in the second case, the two nitro groups are substituted at meta position and para position. So, this is ortho position, this is meta position and this is para position. So, in this case, the nitro group which is present at meta position, it does not contribute towards enhancing the reactivity of the molecule. So, now it is clear to all of you. So, obviously, this one will show the reactivity with more readiness. Okay. Then go to the number 3 question. What is the question? You please see. Which one of these two has more reactivity, methyl chloride or chlorobenzene? So, you just guess and I will tell you the answer if you can't. So, from these two compounds, methyl chloride and chlorobenzene, methyl group is a alkyl group and phenyl group or C6H5 group is a aryl group. As we have already discussed, the methyl groups, if attached, they are very much prone to the nucleophilic substitution reactions. So, methyl chloride will show the reaction more readily, whereas C6H5Cl does not. So, your answer is this is more reactive than the other. Okay. So, I had just discussed only 1, 2, 3 examples. You please work out with more number of examples to clarify your knowledge. Okay. Then students, now we are going to a different aspects of the reactions of aryl halides. The heading is there, electrophilic substitution reactions of aryl halides. I had told you before that the benzene ring is itself a source of electrons. So, because it is very much reactive towards the electrophiles. As we all know, the electrophiles are the electron lovers. So, they get attracted towards the electron cloud of the benzene ring and electrophilic reaction takes place easily. And as you have seen in the screen, the electrophilic substitution reaction takes place in 3 steps. The first step is the generation of the electrophile, then second step is attack of the electrophile by the pi bond of the aromatic group, and the third step is deprotonation adjacent to carbocation and restoring of the aromaticity of the benzene ring. And here I have given you the mechanism of the simple benzene ring with a electrophile. What happens? The mechanism you please see at the slide, the benzene ring and the electrophile is there. The electron cloud of the benzene ring, it attacks the electrophile and forms a sigma complex which again undergoes proton transfer for restoring its aromaticity. So, this is the case for a pure aromatic compound, pure benzene. But in case of a chlorobenzene, what happens? The presence of chlorine, it affects the reaction, because chlorine being a electronegative element, it withdraws the electron cloud towards itself. So, in this case the amount of the magnitude of negative cloud on the benzene ring, it decreases to some extent. However, because of the resonating structures of the chlorobenzene, the positions like those ortho positions and para positions with respect to the chlorine atom, those positions are more susceptible for the electrophilic attack. So, you please go through all these resonating structures. So, you just study these resonating structures. What had happened here? The chlorine atom has lone pair of electrons with which undergo conjugation throughout the ring, and so it is evident from all these structures that in the ortho position and in the para position minus charges are there. So, steric hindrance at ortho positions gives para product at the major one, but products will be obtained at ortho position as well as the para position. Then we will discuss some of the basic reactions like halogenation. First we will discuss about the halogenation process. So, the halogenation of chlorobenzene, suppose we want to add another chlorine atom to the chlorobenzene group, then along with chlorine molecule we will have to take the help of FeCl3, because in the presence of FeCl3 the Cl molecule undergoes heterolytic cleavage to produce a chloronium ion, the Cl plus. So, the Cl plus, the chloronium ion, it attacks at the ortho position to give us 1,2-dichlorobenzene, and also it attacks at the para position to give 1,4-dichlorobenzene. And whenever we will compare these two, you will see that in comparison to 1,2-dichlorobenzene, 1,4-dichlorobenzene is more stable because of two reasons. The first reason is the symmetric hindrance. The first case is the steric hindrance, and second thing is the symmetric nature. What do you mean by steric hindrance? In the first case, the two Cl atoms present side by side, but in the second case they are present apart from each other. So, the para position, the para product is more stable in comparison to the ortho product. Okay. So, there are also other examples of the electrophilic substitution reactions, which we will discuss later. So, please students, now recap all the things which we had discussed throughout our discussions. The first thing is that I had given you the comparative account between the reactions of alkyl halides and aryl halides. Students, after halogenation, I want to tell you about nitration. You please see the mechanism. For nitration of chlorobenzene, we need concentrated nitric acid and concentrated sulfuric acid. As all of us know that the first stage of this electrophilic substitution is generation of the electrophile. So, here is the mechanism to show you the generation of the electrophile. You see, this is nothing but the structure of sulfuric acid. Sulfuric acid is a strong acid, it gives the H plus ion and gives us the HSO4 minus ion, and this is the structure of the nitric acid. In this case, the lone pair of oxygen, they take the H plus ion along with it, and this is the product obtained. So, O plus, as the oxygen shares its electrons to take the proton with it. So, now this bond pair of electrons go to the oxygen atom and it is released as H2O and the product is NO2 plus the nitronium ion. So, once you had understood the formation of the electrophilic component, then you can finish the example easily. So, chlorobenzene, what happens? It takes one NO2 group at the ortho position and it takes another NO2 group at the para position, and as you had seen, the product with the NO2 group at the para position is more favorable than the other one. Okay. So, students, we will go on more about this chapter later, and today let us revise what we had discussed throughout this lecture. First, we had discussed about the structure of benzene. Second, we had discussed about the electrophiles, the nucleophiles, then the reasons behind the low reactivity of the haloarenes towards nucleophilic substitution reactions. Then also we had seen some reactions, nucleophilic substitution reactions which take place under drastic conditions. Also thereafter we had seen the presence of the electron withdrawing groups, and thereafter we had also seen the aromatic nucleophilic mechanism, and lastly we had concluded this chapter with electrophilic substitution reactions. So, I think for today we should stop here and we will again meet in the next class.